All right, so we talked a little bit about acceleration when we were talking about velocity versus time graphs. Okay, and so it's kind of fitting to get into it now because we've talked about what it looks like on a graph. So accelerated motion is any time the velocity of an object is changing. Okay, so that's kind of the first thing we need to understand is what is acceleration, and it is any change in velocity over time, right? Positive or negative. Remember, we don't use the word decelerate in physics. Okay, there is just acceleration. All right, we need to learn the relationship between change in velocity, distance, time, and acceleration. Right, last year, all you learned in terms of acceleration was the relationship between change in velocity and time. Okay, we're going to be going over many more formulas in Physics 20. If you look at your formula sheet, there's a whole bunch of acceleration formulas, not just the one you learned last year. Okay, which actually makes it easier to solve acceleration problems because you have a wider gamut of choices for solving it with. Okay, and then obviously, last thing, be able to solve accelerated motion problems. Okay, so as I said here before, the strict definition of acceleration is whenever the velocity of an object is changing, we say the object is accelerating. Okay, the meaning of average or uniform acceleration, okay, is best illustrated by a plane as it's taking off. Okay, a plane accelerates far more uniformly than a car does. Okay, why is a car not a good example of uniform acceleration? Anybody in here drive a standard? Wow, that's way more hands than I expected. Good for you. Okay, so your car has gears, and even if it's an automatic, it has gears, unless it's a CVT and then it has different stuff. But anyway, okay, if it has, they all have gears, and as a result, the lower gears can produce greater rates of acceleration than the higher gears. That's why if you're passing somebody on the highway and you floor it, the car gears down. Okay, so that it can get a greater rate of acceleration to get you around the car in front of you. All right, the worst thing you can do is try to pass that person without changing gears because that usually results in bad things happening. Okay, so we want to have greater rates of acceleration. But with a car, because you have gears, okay, a velocity versus time graph for a car accelerating tends to look like this. Okay, first gear, we accelerate really well. Second gear, we accelerate pretty well. Third gear, not quite as good as first gear, but still pretty good. Fourth gear, yeah, pretty good. Fifth, it's really good. Sixth, you practically no acceleration whatsoever. Okay, especially if you drive a standard, okay, if you're in sixth gear and you put the pedal to the floor, basically nothing happens. Okay, it just goes, and you don't accelerate. Okay, so you shift down. Sometimes you do the big shift from 6 to 4. Okay, and you come over. If you drive a standard, a bunch of you probably just looked at me and went, "What is he doing?" Because almost no one drives standards anymore. But anyway, okay, so it's not a good example of uniform acceleration because it isn't uniform. Okay, a plane's graph looks a lot more like this because a plane doesn't have gears. It just has the big engines. Push the throttle forward and they just exert more and more force and off you go. All right, so the formula that you learned last year is the one that relates change in velocity, change in time to acceleration. Okay, and acceleration is actually a vector quantity, so there should be little arrows over all of these. Okay, so acceleration is the change in velocity, that's final velocity minus initial velocity, divided by the change in time. Okay, so over time. That's the one you used last year. All right, questions on what acceleration is? Right, so the definition is it's a change in velocity over time, and that's what the formula says as well. And we looked at that the other day, and we said that that means that acceleration is the slope of the line on a velocity versus time graph. Because when we have this, m equals y minus b over x, okay, and we're solving for the slope, okay, there's y, it's vf, okay, here's b, it's VI, okay, and X is time, okay? So distance over, change in velocity over change in time. All right, everybody with me on that? Okay, so let's say we have this plane here, okay? It starts at time 0, it's at rest, Okay, that's one of those terms that you need to be familiar with. At rest means not moving. Okay, so the velocity anytime something is at rest is 0. So if something starts from rest, its initial velocity is 0. If it comes to rest, its final velocity is 0. Okay, but anytime you see the word rest, you know the object is stopped. Okay. All right, so it's going to start from rest, and over a 29-second period, it is going to accelerate from 0 to 72.2 meters per second forward, okay, or positive 72.2. Okay, we want to determine the average acceleration of the plane. All right, we want to write down our givens. Here's where writing down givens is so important. You're going to have like 6 different acceleration formulas to pick from. Writing down your givens will very quickly tell you which one you need to use. Right? I'm looking for acceleration. I have initial velocity, I have final velocity, and I have time. Okay? All I have to do now is go to my formula sheet and find a formula that has those things in it. Right? And it's going to be the one you used last year in Science 10, A equals VF minus VI over T, and we don't have to manipulate it. It's already set up to solve for this. So we put in there our 72.2 minus 0 divided by 29. Whoop. All right, so we're getting that this is going to be roughly 2.5 meters per second. Okay. Everybody follow me there? All right. Now, sometimes I have people ask this question, and it's a valid question, right? They look at this, they see that VI is 0, and they tell me, Mr. Coderre, that answer should only have one significant figure. Okay. And while I understand where that comes from, how accurately can I measure nothing? With absolute certainty is the answer. Okay, if I have nothing, I am 100% sure that I have nothing. Okay, so 0, when it's saying like at rest, it has an infinite number of significant figures. It doesn't affect your significant figures. You're sure you have nothing. You can't count nothing. Okay, everyone follow me there? Okay, because sometimes that comes up. I just want to clarify. All right, so this is what we just did. Okay, we took the formula, we plugged in our numbers, we got positive 2.5 meters per second squared. Now, remembering here, guys, that the units, okay, doesn't mean that it's actually squared. Okay, when I do this formula, okay, remember that I'm dividing meters per second by seconds. So my units for acceleration are meters per second per second. Okay, that means meters per second divided by seconds over 1. What do you do when you divide fractions? You invert the second one and then you multiply. So you have meters per second times 1 over seconds. That means meters, seconds times seconds is seconds squared. Meters per second is usually written as meters per second squared. Okay. All right, so that's where those units come from, in case you had forgotten. Okay, here are the other 4 acceleration formulas that we are going to use in this course. Okay, the first one involves displacement. Okay, so displacement is part of it, and this should actually have like an arrow over top of it. They all should, because they're all vector quantities. Okay, they're all on your formula sheet, so you don't have to worry about that. Okay, so the first one says that displacement equals the initial velocity times time plus 1/2 AT squared. Okay, now if you recall, the other day when we were talking about graphing, we said that basically all formulas are derived from a graph. Okay, this one solves for displacement. How do we solve for displacement on a velocity time graph? So let's say I've got a velocity versus time graph that looks like this, right? And this is like, I don't know, 2, and this is 0, and this is 8. This would be like, I don't know, 10. Okay, how would I solve for the displacement of that object? Right, I use the shapes, right? The area underneath the line. All right, so I would have a rectangle and this triangle. Everybody all right with that? Okay, so to calculate this area here of the rectangle, I would take 2 and multiply by 10, right? Okay, is 2 the initial velocity? Right, at time 0, it's going 2 meters per second. And it does that for 10 seconds. Now, look at this formula again. D equals VI times T plus 1/2 AT squared. That calculates the area of the rectangle. Right? And the 1/2 AT squared is the same as doing base times height over 2. Okay? Because you've got seconds and seconds times squared. Okay? And you're taking half of the acceleration. Okay? So half of the slope will give us actually the area of this triangle as well. Okay? Everybody with me there? Okay? That's where that formula comes from. Actually finding the area underneath the line. Okay? The next formula works the same way, except it starts with VF. So we got D equals VF times T minus 1/2 AT squared. So if we're looking at that same graph, okay, what it's saying is take the final velocity, that's this number here, and multiply it by time. So it's finding this whole big rectangle here. And then it's going to subtract this, which is going to leave me with the area under the line again. All right, so it works. It's, again, derived from graphing. Okay, that's where those come from. Okay, and then the other one, I'm not going to show you how it's derived because it's a mess, but okay, we've got one that has final velocity, initial velocity, acceleration, and displacement in it. It actually doesn't have time in it, which is nice. You actually have a formula that you can solve for things with acceleration that doesn't need time. Right? Once in a while you run into a problem and you don't know what the time is. Okay, this is a formula that can be used there. All right, and the last one is really just this. It's really just average velocity times time. Okay, we don't use it that much because it can only be used for a nice straight line. Okay, because it assumes the acceleration is uniform. So taking the average velocity, that is the final plus the initial over 2, okay, that'll give me the average times time. Right? We don't use it that often because, again, it's not as practical, right? But we will use it occasionally. All right, questions on the formulas there? Okay, what I'm going to do now is I'm going to walk through an example or two of each formula, show you how we manipulate it, okay, all that kind of stuff, so you've seen them all, and then we'll practice a few examples after that. Okay. All right. Okay, so here's our first example. I would suggest probably should write that, write that one down. Okay, I'll give you a second to write it down. Okay, so as with any problem in physics, the first thing we do is write down what our givens are, right? So it says this hybrid car has an initial velocity of 10 meters per second east. Okay, and it accelerates at 3.0 meters per second squared east. So that's my acceleration. Okay, how long will it take the car? So how long is time? So that's what I'll be looking for. Okay, to reach a final velocity of 25 meters per second east. All right, so everything's east, so I don't have to worry about any positives or negatives here, so that's nice. Okay, what formula am I going to have to use if I'm looking for t? I have both v's and a. Which one do you think? Mason, which formula am I going to use? Right. We're going to use change in velocity over change in time. Okay, so that's going to be VF minus VI over T. Okay, that's the formula we got. But we're solving for T. Right now, T is on the bottom of that equation. I cannot solve for it there. So how do I get it to the top? Multiply it. Yeah, so I'm going to bring it over here. So I'll have A times T equals VF minus VI. In other words, acceleration times time equals the change in velocity. Now, I want time by itself, so what do I do with A? Divide it over the other side. All right, so now I've got my formula. So guys, if this was a problem on a quiz, you'd get 1 mark for your givens, you'd get 1 mark for selecting the right formula, you'd get 1 mark for manipulating the formula, you'd get another mark, sometimes, not always, but most of the time, okay? You would get a mark for plugging in your number, so that's going to be 25 minus 10 divided by 3. Okay, so 25 meters per second east minus 10 meters per second east divided by 3 meters per second squared east, right? So we got 15 over 3. The time should be 5.0 seconds. So that question would be out of between 4 and 5 marks, right? Which is why it's important to show your work. All right. Questions on how that one worked? Okay, you would have had questions just like that one in Science 10. Okay, you would have done ones like that. Okay, anyone still need this one? Yeah. Okay, so they're just like the one we just did, except you're going to be solving for different things. All right, so we're looking for, for number 1, we're looking for time again. Okay, number 2, looking for maximum velocity. Now, in number 2, you have kilometers per hour, but you have an acceleration in meters per second squared. So you will need to convert the kilometers per hour to meters per second. Hopefully you remember how to do that. If not, I'll go over it when I go over the question in a few minutes. So the trick here to number 2 is you have to do what's called a compound conversion in order to convert kilometers per hour down to meters per second. Okay, so we set up a compound conversion like this. All right, we have, what was it in kilometers per hour here? So we have 20 kilometers per hour. Okay, I need to convert the kilometers to meters and then the hours to seconds. So first thing I'm going to do is multiply by a conversion factor that will get my kilometers to meters. How many meters in a kilometer? 1,000. Okay, so I write up here that there are 1,000 meters, because I would have to multiply kilometers by 1,000 to get meters. 1,000 meters in 1 kilometer. Now I have kilometers on the top, kilometers on the bottom, and they're gone. Now I've converted it to meters. It's 20,000 meters. Okay, then I need to convert the hours to seconds. In 1 hour, there are how many seconds? 3,600. Okay, so now I've got an hour on the top, hours on the bottom, and it cancels. Okay, so I have to take my 20, multiply it by 1,000, and then divide it by 3,600. So in other words, I'm doing this, 20 times 1,000 over 3,600. Can I simplify that? I can simplify it like this, right? Be the same as doing this. Okay, so can I just go 20 divided by 3.6? That's how you convert kilometers per hour to meters per second. Divide by 3.6. You want to go the other way, you multiply by 3.6. Okay, so to convert kilometers per hour to meters per second, divide by 3.6. To get meters per second to kilometers per hour, multiply by 3.6. All right, give you a few more minutes to get number 2 finished now that you can do that part of it. Mhm. All right, so for number 2, we want to write down our givens, but we do want to convert our velocities into meters per second. So we're going to go 20 divided by 3.6. Oh, okay, is 5.5 repeating. Okay, meters per second, and that's north according to the question. Okay, it accelerates at 1.5 meters per second squared to the north. Okay, for 9.3 seconds. Okay, we're looking for its final velocity. So different manipulation on this one. A equals VF minus VI over T. Okay, so if I want to solve for VF, first thing, okay, so we go through our rules of algebra here, right? If I want to move something, I do the opposite. What I do to one side, I do to the other, and I move what's not attached first. T is not attached to VF, so I'm going to move it first. So I'm going to multiply both sides by T, okay, and then I'm going to add VI over there. So VI plus T times A equals VF. All right, so we'll have 5.5 plus 1.5 times 9.3, okay, and that'll give us our final velocity in meters per second. So, not times, plus 1.5 times 9.3. Okay, so there's my final velocity in meters per second. I need it in kilometers per hour. Okay, 70.22 meters. So, and then we only have 2 significant figures here, so it'll just be 70. Okay, kilometers per hour. That's a pretty fast elk. Okay, everybody all right with that one? Okay, let's look at this example here. So we're going to write down our givens, and then we got to figure out what formula to use, because it's not going to be the same one. So I have a cattle train that is traveling west at 16 meters per second. So that sounds like that's the way it starts. So 16.0 meters per second and west. Okay, it is brought to rest. What does that tell me? That it stops. So VF is 0. Okay, and it does so in 8 seconds. Okay, we are looking for the displacement of this cattle train. All right, I don't have the acceleration. I have VI, I have VF, and I have T. So do I have a formula that has those 4 things in it? Okay, which one is it, Lexi? Okay, someone find it on their formula sheet? Close, but I need the special version that we just looked at a minute ago. Okay. Not minus, but plus, right? So we're going to do this. VF plus VI divided by 2 times T. Okay, it was the last formula on that one slide there, right? So this does deal with the fact that velocity is changing. That's reflected here. It's still an accelerating object, okay, but it'll help us to get displacement with those 2 things in time. All right, I don't have to manipulate. It's already set up to get the displacement, okay, of this object. All I have to do is plug in. So VF was 0, okay, VI was 16 over 2, okay, times the time, which was 8 seconds. All right, so I've got 16 divided by 2, which is 8, times 8 is 64. So the displacement while slowing down of this cattle train is 64 meters west. Okay. All right, now let's have a look at how we manipulate this formula for other things. Okay. All right, what if I want to solve for t? T's already on the top, right? So I can leave it over here. How do I get all of this over to the other side? I could, but there's a simpler way. Is this all in brackets? Can I move it all at once? It's just a number, right? I would do all of this before I did anything else according to order of operations. So can I just divide that whole bracket over to the other side? Right? I'm multiplying this by t. If I want to move it, I do the opposite. I can do whatever I want as long as I do it to both sides. Okay, so I'm going to divide the whole thing over to this side. So d over vf plus vi over 2 equals t. Okay, this, guys, is the same as this. Right? When we manipulate v equals d over t, that's what we get. Same thing here. Average velocity, displacement divided by average velocity equals time. Okay. All right. What if I want to solve for VF? What should I move first? If I want to solve for VF. Yeah, I should divide by t. All right, so I'm going to bring t over here first. All right, now t is gone. Do I need the brackets anymore? Nope. Okay. I want VF. What do I do with the 2? Multiply it. What do I do with VI? Subtract it. 2 times d over t minus VI. All right, guys, so this is average velocity minus initial velocity equals, okay, we got her. We're all good. Okay. All right. That making sense? How we would manipulate that one? Okay. Those two problems deal with that formula. Give them a try. See how you do. All right, so for number 1 here, guys, okay, we know that the initial velocity is 16 meters per second south. Okay, so we have VI, 16 meters per second south, and then it slows down uniformly to a velocity of 4 meters per second south. And it does that in 4 seconds. Okay, we are looking for the displacement of the hound during that time. So D equals VF plus VI over 2 times T. That's the only formula that we have enough information to use. So we will just plug in the numbers because it already solves for what we're looking for. So we have 4 plus 16 divided by 4, and then times, sorry, over 2, not over 4, times 4. Over 2 times 4. Okay, so 4 plus 16 is 20, divided by 2 is 10, 10 times 4, the displacement is 40 meters south. Okay. How many people have done number 2? Okay, do we need to go over number 2? Yes? Okay, go over number 2. All right, so on number 2, we have a ball that moves up a hill, and this one's a bit tricky because you have to take into account that if a ball is moving up a hill, it is accelerating down the hill, right? Okay, it can move up, but it's accelerating down. Its acceleration is negative. Okay, so the ball moves up a hill with an initial velocity of 3.0 meters per second uphill. Okay, a little while later, it's moving down the hill at 9 meters per second. Okay, and we want to find the displacement of the ball from its initial point of the release, and we know that the time is 4 seconds. Now, a question usually comes up here. They wrote it like this. How do I do a significant figure calculation with that? I don't know how many significant figures FOUR has. Okay, if it was 4, the number, I'd know it had 1. Okay, but in this case, I have to assume it has no effect on the significant figures because I just don't know. right? So I go by all the other actual numbers I was given, and I consider that 4 seconds to be a counted number, okay? And counted numbers have no uncertainty, okay? Everybody follow? That's a weird situation. It's like the only time you'll probably ever encounter it. All right, so I'm looking for D. So again, we just got to plug in our numbers here. Okay, so we have 3 plus, not 33, okay, plus negative 9.0, okay, divided by 2, okay, times 4 seconds. Okay, so 3 plus negative 9 is negative 6, right? Divided by 2 is negative 3 times 4, okay, is negative 12 meters, but I can't write it as negative 12. They did, but they shouldn't. It's wrong. Okay, it should be 12 meters downhill because that is what the question gave us. It did not give us positive and negative. It gave us uphill and downhill. Okay, questions there? All right. Write that one down, give it a try. See if you pick the right formula to use for that one from the new ones you have. Okay, let's look at this one before the bell goes here. So we have a golf ball that's traveling at 25 meters per second. So we're going to say that that is its initial velocity. It doesn't give me a direction, but I'm going to make it positive. Okay. Hits a sand trap and slows down with an acceleration of negative 20 meters per second squared. Okay, find its displacement after 2 seconds. All right, do I have a formula that has VI, A, D, and T in it? Okay, first one we talked about today. Okay, D equals VI times T plus 1/2 AT squared. That's the one that calculates the area underneath the line on a velocity time graph. All right, so when we plug in our numbers here, we will have 25 meters per second times 2 seconds plus 1/2 times negative 20. It's key that you put the negative in here or you get a ridiculous answer that says by slowing down the golf ball speeds up. Okay, and then times 2 squared, right? That'll give us our final answer. So 50 plus 0.5 times negative 20 times 4. Okay, its displacement will be 10 meters forward, or positive 10 meters, because they didn't really tell me otherwise. All right, remember guys, lab report due on Wednesday of next week, so it might not be a bad idea to look it over on the weekend and do a little bit of it.